Okay, guys, we're going to talk about the isosceles right and the 30-60 right triangles today. This is an extremely important lesson for you as you're getting prepared for trig for next year. So please take note of what's going on, make sure you understand, and get into the chat room if you have questions. Here we go. First thing we're going to take a look is the isosceles right triangle. In the isosceles right, we're going to use Pythagorean theorem to kind of show you where the theorem comes from that we're going to talk about. In this isosceles right that has side lengths of 1 and 1, we're going to take the 1 squared plus the 1 squared, which is just 1 times 1, set it equal to c squared. So using Pythagorean theorem, we simplify by adding the 1s to get c squared equals 2. When you take the square root on each side, you end up getting radical 2 or 1 radical 2. On the blue rectangle or triangle down here, we're going to take a look, and 2 squared plus 2 squared, well, that's 4 plus 4 is equal to c squared. You add those together, you get 8 is equal to c squared. And when you simplify the radical 8, you're going to get 2 radical 2. On your purple triangle up here at the top, the 3 squared plus 3 squared is 9 plus 9. You get 18 when you add those together. So 18 is equal to c squared when you take the square root on each side. 18, radical 18 simplifies into 3 radical 2. The final example I'm going to take a look at here is the green triangle at the bottom. You're going to square the legs. A squared plus b squared, or 4 squared plus 4 squared is 16 plus 16. Add those to get 32. So c squared is equal to 32. And then when you take the square root, you end up getting 4 radical 2 for the length of your hypotenuse. That all leads us into this theorem about the isosceles right triangle that says in isosceles right triangle, the hypotenuse is radical 2 times the length of the leg. So if I go back to where we were, you can see the pattern develop. Every time I did the Pythagorean theorem, I took the leg length of 1 multiplied by radical 2. Well, that gave me the hypotenuse. Took the leg length of 2, multiplied it by radical 2. That gives me the leg length of, or the hypotenuse length of 2 radical 2. So the leg of 3 times the radical 2, 3 radical 2. So the pattern develops of what this theorem is talking about on that last slide, that you take the leg times radical 2 to get the hypotenuse in the isosceles right. The corollary is talking about a square. And if I draw a diagonal into a square, it's not hard to imagine that it would divide it into 2 isosceles right triangles. So it makes sense that the diagonal of the square is radical 2 times the length of one of the sides. Probably can live without having this particular corollary just because it's so closely related to the theorem that you should probably just see the theorem when you look at the square with the diagonal drawn in it. Let's use this in some examples. First thing I want you to think and realize is the ratio of the sides. When you have got a isosceles right, the ratio of the sides is 1 to 1 to radical 2. That's the leg to hypotenuse, 1 to 1 to radical 2. And the key number, the important number here is the radical 2, because in the ratio of 1 and 1, the ones you multiply and divide by, they're not going to do anything as far as changing any lengths of numbers or sizes of numbers. So we're going to plug these numbers over here just to kind of give us a visual. And this is representing the ratio of my sides. Well, if I take the 12 to get the other leg, well, since they are equal to each other, this leg here is just simply going to be 12. And then to get from the leg to the hypotenuse, well, the theorem we had just said to take the leg times radical 2. So I multiply by radical 2, and I get 12 radical 2. It makes sense that I would multiply because I'm going from a leg. I'm moving to the hypotenuse, which is a larger side. And if I multiply, that's going to make it larger when I multiply by radical 2. The reason I'm saying that is on this next example, I have the hypotenuse, and I'm going backwards to get to the leg. Well, if I multiplied leg times radical 2 to get the hypotenuse, I'm going to divide the hypotenuse by radical 2 in order to get the leg, because we're going the opposite direction, so we're going to use the opposite operation of division. Well, when I divide by radical 2, I rationalize my denominator like we learned back in our algebra days, and I end up with radical 2 over 2. Before some of you jump out of your seat there to go grab a calculator, I want you to be able to do all of these without a calculator. And matter of fact, I want to get to the point where hopefully you can be pretty efficient with it and do them rather quickly, almost like your times tables back in elementary school. Anyway, here we go. Taking a look at this, 15 is the hypotenuse. You've got to divide the 15 by radical 2 to get to the leg, just like we talked about on that last one. So as we divide by radical 2, once again, we need to rationalize multiplying top and bottom times radical 2. So my final answer here for the legs is going to be 15 radical 2, and then radical 2 or radical 2 times radical 2 on the bottom just gives me 2. So I got 15 radical 2 over 2. Taking a look here at the next three examples. This is the corollary that was talking about finding the diagonal, which essentially it's just an isosceles right triangle. So this whole multiplying by radical 2 to get the hypotenuse is going to work. The exact same thing that corollary is saying. So I don't necessarily look at the corollary. I just say, oh, I've got an isosceles right. I'm just using my 1:1 radical 2 ratio. And here on the leg, well, that would also be 7. Well, if this leg is 1/2, we know the other leg is also going to be the same thing as 1/2. Well, to go from the leg to the hypotenuse, it's going from a leg to hypotenuse. It's getting bigger. So you should think the operation is multiplication. So I take the 1/2 times the radical 2. And remember when you had fractions back in the day, you could divide anything by 1. And you end up with radical 2 on the top and over 2 on the bottom. So the easiest thing to think of is this, though. If you're multiplying a fraction times some number, that number just goes in the numerator. If you're dividing a fraction by some number, that number would go in the denominator. So let's take a look at the next one here. I'm going from the hypotenuse. I'm moving to the leg. So I'm dividing. So as I divide, remember we just said that we would take and divide by radical 2. And when you divide a fraction by some number, that number goes in your denominator. So I put the 2 down on the bottom. And then you'd multiply top and bottom times radical 2 to rationalize this guy. And we end up with on top 2 radical 2. And that's over 2 times, or radical 2 times radical 2 is 2, times 5 is 10. So in this one, since these numbers outside will reduce, we go ahead and do that because you can reduce numbers inside the radical and numbers outside. So the numbers outside reduce to 1/5. So your final answer is radical 2 over 5. At this point, I'm going to go ahead and show you 6 more examples. I want you to go ahead and try these on your own. I'm going to have you pause the video, and as soon as you start the video up, the answers are going to appear here in just a moment. Okay, guys, use these problems as a little self-check. Hopefully your answers are correct. If you're struggling on these, by all means, I would suggest getting into the chat room. Let's go ahead and take a look here, though, at our next slide with our next theorems. So the next theorem, I'm talking about the 30-60 right triangle. In the 30-60 right triangle, it says the hypotenuse is twice the shorter leg, and the long leg is radical 3 times the short leg. So the hypotenuse is twice the short leg, and the long leg is radical 3 times the short leg. So in this triangle, they're relating everything back to the shorter leg of the right triangle, or the leg that's opposite the 30-degree angle. We'll take a look at examples to explain what that's talking about. And then off of that particular theorem, the corollary comes, which gives us a couple of formulas essentially. And it says an altitude of an equilateral triangle having side length s is radical 3 over 2 times the side. So this only works for an equilateral triangle, but this is a formula, radical 3 over 2 times the side length, that will find the altitude if I know what the length of the side is. And then here is a formula for area, and it says the area is radical 3 over 4 times the side squared. So once again, if I have an equilateral triangle, I know the length of one of the sides. You don't have to use your area formula for a triangle. You can just use this simple and convenient little formula and plug in the length of the side, and you would have your area. All right, the first thing we're going to take a look at some problems with the 30, 60, 90 and how to find the lengths of sides using what that theorem tells us. And essentially what it tells us is the ratio of the sides is 1 to radical 3 to 2. 1, radical 3, and 2 is the length of the sides in order. This is the shortest side, or the short leg. This is the long leg, and 2 represents the hypotenuse. So opposite the 30-degree angles, my short leg, the long leg is the radical 3, and the hypotenuse is 2. So using those ideas, some people, it's beneficial for you to even draw right into your diagram this ratio of the sides, just so it kind of gives you a little visual. And as I look at this, everything relates to the short leg. So I'm going to take, well, the 5 to get to the hypotenuse, the ratio is 1 to 2, or the key number is the 2. And since it's going to the hypotenuse, it's getting bigger. So the 5 times the 2 is going to give me a hypotenuse length of 10. And here I'm going from the short leg to the long leg. The key number is the radical 3, because multiplying or dividing by 1 doesn't do anything. I'm going to multiply the 5 times this radical 3, and that tells me the length of that long leg is 5 radical 3. On my next example, I've got the long leg, and if I label my sides again like we did on the previous one, this is the side, the 1, this is the radical 3 side, and this is the 2. And remember, I said every time we look at these, we want to compare a side to the short leg. So this side of 1 to the short leg here of y. Well, in order to get it, I'm going from leg, long leg, to short leg. Well, I'm getting shorter. I have to divide by the radical 3. So I take this length of 1, I divide by radical 3, and then we're going to have to rationalize this by multiplying the top and bottom times radical 3. And as I multiply the top and the bottom times radical 3, we get radical 3 over 3. So that's the length of y, or the short leg. Now, in order to find the hypotenuse, I don't really want to mess around going from the long leg to the hypotenuse because I have these numbers of radical 3 and 2. It's much easier to work with the ratio of 1 to 2. So I'm going to say, oh, I'm going from the short leg to the hypotenuse. I multiply by 2. Remember what we talked about there on the last examples. When you multiply, the number just simply goes in the numerator. So I take the radical 3, times it by the 2, and my answer here for my hypotenuse is 2 radical 3 over 3. So our answers for the leg, short leg, and the hypotenuse are as such. On this next set of problems, I give you the length of 9, but I put it in all 3 different positions. First of all, I've got the hypotenuse. Remember, we're working through the short leg. The key number is the 2. Well, I'm getting smaller, so I divide by 2, and I get 9 halves. Don't really want the decimal there, just leave it as a fraction, because we typically don't write fractions with radicals, and a lot of answers we get, we're going to have radicals, like right now. Going from the short leg to the long leg, the key number is radical 3. It's getting bigger to go from short leg to long leg, so you would multiply by radical 3. And when you multiply a fraction times a number, that number goes in the numerator. So it's going to be 9 radical 3 over 2. On this one, I have the short leg. We want to work through the short leg to get to each of the sides. The short leg of 9, I multiply by 2 to get the hypotenuse of 18. To get from the short leg to the long leg, the key number is radical 3. So you multiply by radical 3, and you're going to get 9 radical 3 for your long leg. And then finally, on this last example, I've got the long leg of 9. And remember, we don't want to go from the long leg to hypotenuse. We're always working through the short leg. Well, going from long to short, we're going to divide. Key number between those is radical 3. So I'm going to take 9 and divide by radical 3. And we rationalize this denominator by multiplying radical 3 on top and bottom. We get 9 radical 3 over 3. But then the 9 and the 3 reduce, so you end up with the y value here equaling simply 3 radical 3. Remember, when we find the hypotenuse, we're once again going through the short leg. The key number between short leg and hypotenuse is 2. So we multiply by 2, and 3 radical 3 times 2 is just simply 6 radical 3. Much like we did on the previous slide, I'm going to give you these examples here. I'm going to have you pause the video. When you start it back up, the answers will appear, and just check yourself to make sure that you are getting these correct. Okay, go ahead and do a real quick self-check. Probably want to pause the video again so you can see the answers. And I'm going to go ahead and move on to the next slide. On this one, we're using that corollary. We're using that corollary that we had for the area and altitude of an equilateral triangle. And so here I have an equilateral triangle with a side length of 15. So to find the area, all we simply have to do is plug into the formula, and you take the side squared, which is 225, and then you multiply that side squared times radical 3 over 4. And remember, when you multiply by a fraction, the number of 225 that you're multiplying just goes in the numerator. So you end up with 225 over 3 for the area. The altitude for this guy, well, the formula for that's over here. You take radical 3 over 2 times the side length. And since the side length is 15, you're multiplying by a fraction. That fraction of 15 goes in the numerator. So it's going to be 15 radical 3 over 2. Second example here, we've got the length of the side here is 8. So the area for this guy, plugging into the formula, you take the side squared and get 64. And you multiply that by radical 3 over 4, which ends up equaling 16 radical 3 when you reduce the numbers outside the radical. And then finally, your altitude for this guy. The formula tells us to take the side length of 8, multiply it times radical 3 over 2. And as I do that, the 8 and the 2 are going to reduce. So I end up with a final answer here of 4 radical 2. All right, much like the other slides, I got a couple of practice problems here. I already got the solutions worked out for you, but you could pause the video, ignore the answers that I have here, and just see if you can work through using those formulas. Anyway, we'll go ahead and move on to the next slide here. You can pause. All right, and then finally, the last slide here is just your optical illusion for the day, guys. Hope that all this makes sense. I'm only giving you a few examples of each, and I would strongly encourage you, if you are struggling, you've got to get in to see me in the live chat room. This lesson is extremely important for trig. We will do a significant amount of work with this, and going to be a very important concept. So anyway, hope to see you there, and have a great day. Hope everybody's safe.